Let's say you take a ball in your hand and you throw it upwards, just like how we play catch with our friends, isn't it? All of us must have played at some point of time. So you take a ball and you throw it up. Okay, it goes up and we know what happens to this ball. When you had thrown it, you have given it some initial velocity, but as it is going up because of this value of velocity that you have provided in this upward direction, it is also experiencing a force in vertically downward direction, and this pull is the pull because of the earth, and this force is no other than the gravitational force. So the motion while it is going up is a retarded motion, and as it goes up at the highest point, we see that it stops momentarily and then it changes the direction and it starts coming down, right? So you throw it, it goes up, it comes back. Whatever we throw, it comes back, right? So it's a common saying that what goes up must come down, until and unless it has been thrown with a particular value of velocity, which we call as escape velocity. So let us say you throw it with more strength, it goes even higher, even more, even higher, with such a strength that the initial velocity that you are imparting it is approximately around 11.2 to 11.6 kilometers per second, then the thing is never gonna come back to the earth. All right, it's not going to return back. It has escaped the gravitational influence of the earth, and this velocity that is required to go out of this gravitational influence is what we called as escape velocity. No problem. So if you have a cannon and it is powerful enough, okay, so I'm just trying to use an example to show you that what it means to go outside the influence of the earth's gravitational field. So you throw this, you have got so much of impact that you can provide it with some velocity. It will go up. We know that after a point of time it goes to some height and probably it will fall down, but then you give it even more push, right? Even more velocity, initial velocity, you go on increasing it till it reaches to a value, as I told you, equal to 11.2. In some books they also write it as 11.6, but you know, approximately that range you can take. Kilometers per second. This is never coming back. It has escaped. So what should be the value? We know the result, but how do we calculate it? In physics, we want to know the formulas, that how did you got to that value? Why only 11.6 in case of the earth, or 11.2 in case of the earth? Why not something else? What would it be for moon, let us say, or maybe for some other planet like Mars? Will it be same? Will it be different? On what factor does it depend upon? All that coming up next, so buckle up, keep your notebook and pen ready. Let's get started. Let's start analyzing what happens if you have a cannon like this and you just project a ball like this. What will happen after some time? It will just fall down somewhere over here, right? Okay. Now, if it would not have met the earth, it was just let to, if it was just made free to move, it could have completed this trajectory, which could be elliptical or circle. You given more value of initial velocity. What will happen then? Then it goes even further. And then if it was let to just go around, it would have followed the trajectory like this, okay, circular or elliptical. Further, what happens then? Well, if you have just projected with some value, some particular value of velocity, it will just keep on moving in a circular motion. Now that happens in case of satellite, and we are yet to study about satellite, but this is exactly what happens when we are planning to launch it in some particular designated orbits. So it goes on moving like that. But is this value of velocity that we have given, which you see that it is not falling on the surface of the earth, can I say that this is the escape velocity? Can you say that this is what we call as the escape velocity? Probably not. This is not the escape velocity. Remember, from the definition, we understand that escape velocity is something when a body has got the minimum value of initial velocity such that if you project it with that velocity, it will surpass the gravitational influence of the earth. In this case, even though this particle is moving around the surface of the earth, okay, in a circle, let us say, still, it is still at any given point, because of the velocity it wants to move like this, but because there is a gravitational force, it keeps on following this curve, right? It goes on falling down, but it does not meet the curve itself. That's the reason, okay? So what happens? It just goes in a circle. When we project it with some value of specific initial velocity such that it surpasses the gravitational influence of the earth, and we say that it has gone to infinity, let us say. Okay, now remember that infinity is a relative term, and I have taught you many a times, I have told you this many a times. So it has now gone out of the influence of the earth's gravitational field. That is when we say that the velocity with which you must have projected it, v initial, is equal to the escape velocity, v. No problem. Got it? First of all, the idea of escape velocity should be clear. What is the idea of escape velocity? It is to go out of the field, that is the gravitational influence of the earth. No problem. Okay. So now let's check out what will be this value, because now we know so many aspects of gravitation, probably we should be able to calculate this, right? Okay. So let us say from the surface, I project it with some initial value of velocity vi, and I'm saying that it has got a value of velocity such that it is never returning back, which means it has escaped the influence or the gravitational influence of the earth. So this has gone, let us say, to infinity, right? Now we know that we have projected it from the surface of the earth. So this distance from the center of the earth can be taken as what? Radius of the earth. Let us take it as RE. Let's say the mass of this ball is m, okay? So if this is our initial condition when this body was on the surface of the earth, and this is the final condition when this has escaped out of the influence of the earth's gravitational field, so can I say that the potential energy over here, u at infinity, is equal to 0? Yes? Sure? Okay. At this point, it can have velocity. Even the velocity can be 0. We just want to give it such a velocity so that by the time it reaches to infinity, even if it is 0, no problem. All right, it just escapes. It just, even if you are giving it more than that, no problem. It will just carry that velocity, not a problem. But minimum value that it should acquire while it reaches to infinity, we can write it equal to 0, no problem. Now, what we can say, that this is the initial condition and this is the final condition. What we can conserve? Definitely we can conserve energy, right? So if I can conserve energy, what will be the initial energy that we are talking about? Well, the initial energy, that is ui plus ki. That is initial potential energy plus initial kinetic energy. This will be the total initial energy. That is going to be, we know the formula, minus G capital M, where capital M is obviously the mass of the earth we are talking about, times small m divided by RE, radius of the earth. Why? Because it is on the surface. Obviously we know that potential energy is negative on the surface. We know this. What about kinetic energy? We have projected it with Vi, so plus half m Vi squared, no problem. This should be equal to the final energy. And what is the value of final energy? Final potential energy plus final kinetic energy. So final potential energy is at infinity. When this body is at infinity, we can say that, well, that is equal to 0. No problem. And a final kinetic energy, we have told that, okay, it can have kinetic energy, not a problem. But in limiting condition, we are saying that just when it reaches over there, the value of velocity finally becomes equal to 0. Just the limiting condition, right? So if that be the case, this is also equal to 0, right? Which means to free anything up, to make a body free of the gravitational influence of the earth, you must provide it with some value of kinetic energy such that this potential energy which is negative can be compensated off. Which means if you are able to give this body some amount of energy such that the total energy finally becomes equals to 0, then that body will be free of the influence of gravitation because of the earth. No problem. Okay, so when this total energy final becomes equal to 0, what I can write? I can write half mv square, that is vi square, is equal to g capital M small m divided by Re. No problem. The small m gets cancelled out. So now can I call this initial velocity is the velocity which is given to this body such that now it has escaped out of the gravitational influence of the earth. Can I say that? Yes. So can I name this as escape velocity? Let's call it as VIE, okay, or VIES, whatever you want to write it, no problem. So the escape velocity VE is equal to root over of 2 times of GM by R. All right, the escape velocity is equal to root over of 2 times of Gm by Re. No problem. Here m is denoting the mass of the earth and Re is denoting the radius of the earth. No problem. The escape velocity can be also written in general form, that is 2 times of Gm of any planet divided by radius of that planet. No problem. Okay. So this is how we get to the formula of the escape velocity. Clear with this? Very simple. What we told, that from the surface of the earth we have got such a cannon by which we can, go on imparting more and more values of initial velocity, right? We can go on increasing. We have got such a powerful cannon with us. So we go on giving it more and more value of velocity. A time comes when the cannonball that we are throwing out is able to surpass the gravitational influence of the earth, and we say that at that point we can say that the velocity that was given, the minimum value of velocity actually required to just surpass that, will be equal to what? Will be equal to the escape velocity. Because why we are saying minimum? Because we are assuming that when it goes to infinity, the value of final velocity becomes equal to 0, not a problem. Okay, fine. Okay, so this is the final relation, the final expression that we have got. That is, in case of the earth, that is equal to root over of 2 Gm by Re. In case of any other planet, you have the same formula, that is root over of 2 times of G, that will remain same. Mass will be mass of that planet divided by radius. Radius will be radius of that planet. You choose any planet of your choice, you are able to find the value of the escape velocity of that planet.